All right, this is our last section of material for this year. Yay, 13.5. We're going to take a look at volume and mass in this lesson. You guys have already done a metric unit in class last week on volume and mass, where you weighed things, right? That was in terms of grams or kilograms. And then where you looked at the capacity, which was the terms of volume. So mass is kilograms or grams, and then the volume that we did was in terms of liters or milliliters last time. So we're going to take a look specifically starting with volume. Volume is the number of cubic units needed to fill a three-dimensional surface. A cubic unit is the amount of space taken up by a cube with measure of 1 unit on a side. So it's a 1 by 1 by 1 cube. So you can imagine something like this. And all the side lengths are 1. Now, for some of the objects that we're going to be looking at, it's very easy just visually count the surface, or not the surface, but the volume. So, for instance, this is an example of a volume picture. We're asked to find the volume and the surface area. We'll start with volume. The volume is the easier of the two things to find. So, taking a look at this, what is the volume of this shape? How many cubes are there? 4. That's all volume is. It's counting the cubic pieces. This is 4. Now, it doesn't tell us what the length measurements are in, right, the units. So we're just going to write units. And volume is in cubic units because it's length, width, and height, right? All 3 units, or all 3 measurement lengths, so that's units cubed. Okay, surface area, a little bit tougher. So if you think about surface area, I would encourage you to think about the fact that there's 3 different surfaces to consider. Now, there's kind of 6, so let me write them all down, and then we'll group them together. You have the top surfaces, and you have the bottom surfaces. You have the left surfaces and the right surfaces. And then you have the, we'll call them front surface and the back surface. All right, so if you had this image in your hand, like Legos, imagine this is Legos, right, the square ones, okay, the ones that look like cubes. And you had this all kind of put together, and you could turn the object all the way around and count the surfaces. You'd have 6 different views in which to look at this. You can look at it from the front, or you can turn around and you look at it from the back. You can look at it from on top down, or you could look at it from the bottom up. You could look at it from the left, or you could look at it from the right. Does that make sense to everyone? Okay. The kicker is, however, that some of these are actually duplicates, right? The top and the bottom, typically speaking, and there are cases where it's not true. I'll mention them when it happens, but almost always the top and the bottom are the same. They have the same surface space. And the left and the right have the same surfaces. Not the same surfaces, but the same number of surfaces. And then the front and the back have the same number. So you typically just duplicate looking from the front, from the top, and from the right, or the bottom and the left, and the bottom and the left and the back, or something like that. So we're going to think about these different sort of images and count what we see. So we're actually going to start with the top. If we were looking at this image from the top down, how many boxes do you see? Like how many squares do you see? You see 3. You see this shape right here. You see this shape right here, and you see this shape right here. But imagine if you were looking at it from the bottom up, how many would you also see? 3. There's 3 blocks along the bottom, and you'd see all of the bottoms of those 3 blocks, right? So in fact, they match, just like we were predicting would happen. So this is 3 plus 3. So let's do it from the left and the right. So this over here is from the right, And again, you're looking at it from a two-dimensional perspective. So while I know that this piece right here exists, I wouldn't see it if I looked at it strictly from the right. Does that make sense? I'd only see this piece right here and this piece right here. There'd be 2. And the same thing from the left. Now these are hidden. You can't see them the way that it's drawn, at least not this one. But there's a shape back here that's over here, right? I mean, I can see that that should be there. And I can see again up here that there should be one here. The left and the right are each 2. How about from the front? There are 4. I've got 1, 2, 3 across the bottom and 1 here in the top. There are 4. And I can't even sort of get at the back of this object. But can you visually imagine that there's also 4 if you look at this from behind? Yeah. So they occur in pairs. If I were to add up 3 plus 3 plus 2 plus 2 plus 4 plus 4, what would I have? I think it's more. Is it 18? 18 is what I have written down, so I think it's 18. 18, and these are the squares I'm adding up, so they're square units, right? So I would write down square units, or in this way, it'd be units squared is what it looks like. Okay, is everybody good with that? Okay, we're going to take a look at another couple of them. So I have 2 objects here. We'll look at object number I, or letter I. Again, volume's the easy one to calculate typically, and surface area tends to be a little trickier. If you're looking at the volume of the first shape, how many do you have? Okay, did everybody get 9? Okay, so we sort of fill in the blanks with what we imagine is there. We do that, and you did it just right, Julie. So while I can only see 1, 2, 3, 4, 5, 6, and 7, we imagine that underneath the blue one, there's another one, and that stack at the back that there's a third one in the bottom. So everybody sort of visualize that okay? There are 9 objects here. So this is a volume of 9 units cubed. Okay, we're going to look at our sides in pairs. We have 2 times the top or bottom, 2 times the right or left, and 2 times the front or back. So I put the ones that I think are the easier of the 2 options to see. So again, and it doesn't matter the order. If you don't want to do the tops first, do the front first, go for it. Okay, so I'm going to do the top. If you look from the top down, how many can you count? How many squares do you count? 6. There's one here, one here, one here, 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 and here. There are 6 from the top down. So 2 times 6. How about from the right-hand side? Yeah, I agree. So we've got 1, 2, 3, 4, and 5. Can you imagine turning the object and would you see all those 5? So 2 times 5. And from the front. What do you think? 6 is right. So I have 1, 2, 3, and then 4, 5, and 6 on the front side of my object. All right, so go ahead and run the calculator if you would like, or multiply it out by hand, either way. What is 2 times 6 plus 2 times 5 plus 2 times 6? I don't think it could be 39 because that's odd, and there needs to be a, what do you have?
I said 49, so I don't.
Okay, it can't be an odd number because I multiplied everything by 2's. 34? Yeah, 34 is right. So this would be 34, and again, I'm counting squares, so this is units squared. Did you find your error, Emily?
Yeah, I did 5 times 5 instead of 10
Oh,
times 5.
yeah, that'll do it. We found it. That's good. Okay, any questions on that one? Okay, our next shape has a little bit of difference to it. You can see how they're showing the blue piece has sort of moved, right? Okay, that is going to change one of our features. Let's talk about volume first, because again, it's the easier of the two options. So object number 2, or double I. What's the volume of my shape? Yeah, it's still 9. The volume did not change by moving one of my cubes. So it's 9 units cubed. Okay, the surface area is going to change by simply shifting that block. What you want to imagine in terms of surface area is, let's imagine you were wrapping this in like wrapping paper. You're putting wrapping paper around all of it. Okay? When you move that blue object over, you now have more surfaces exposed. Don't you? It's kind of hidden because we don't have the object itself to hold, but there is a piece back here from the left-hand side that's there that wasn't there before. It was embedded inside the object before, but now it's on the exterior of our object. So we're going to be a little bit more careful because of the sort of, it's really just because of the gap right here that's causing that. Okay, that gap right there. We're going to be careful, a little bit more careful to do the top, bottom, left, right, all those pieces separately. So we're going to do the surface area, and we have the top and bottom. We have the left and the right, and we will have the front and the back. Okay. Okay, so we'll start with the top since it's listed first. If you look from the top down, how many pieces do you see? Yep, there are 6. And from the bottom up, you still see that same 6, right? Yeah, those didn't change by shifting the blue piece. The left and the right are the pieces that are a little bit different. So if you look at this from the left, over here, you still see the same 1, 2, 3, 4, 5, right? But there is another left piece that you can't see that's hidden on the blue. Are you seeing it now? So there is those 5, but there's this additional 1 that's on the blue side. So the left is almost sort of like 5 plus the one that's hiding on the blue. On the right side, you've got the same problem. You've got 1, 2, 3, 4, 5, and then there's this red one over here that's also now exposed, right? It's a right side piece. It's a piece on the right. You can't see it completely from the right, but it is exposed right here. So I have another 5 plus 1 on the right side because I've got this exposed piece. From the front, how many pieces do I have? Yeah, I have 6. And you can imagine looking from the back, you would also have the same 6. What do you get when you add all these together?
36.
You get 36 units squared. You get precisely 2 more, and the reason that you do is because when you moved that block, we got 2 exposed sides that were previously not exposed. Does that make sense? Previously, they were embedded inside of our object. Any questions on that? Okay. We've seen these in passing once before. You had them on your very first set of metric activity sheets that I passed out. These are English units of volume. So we have cubic feet, we have cubic yards, cubic inches, that's the top part of it. And then we've got our gallon and our quart pints, cups. There's fluid ounces down there at the bottom. And you can see all the different measurements and how they're related. I've mentioned this guy before. He's called Gallon Guy. He's a great visual representation. My daughter was in 4th grade when she created her own Gallon Gal. And it looked like this. And so if it was a girl, they created a Gallon Gal, and if it was a boy, they created a Gallon Guy, and I'm sure they had flexibility if they wanted to do the other one, it probably didn't matter. But they were creating this image, right? And so the idea of this image was that they were going to be able to remember that they've got 4 cups inside of 2 pints inside of 1 quart, right? If they go up the leg. That they can see that they have 1, 2, 3, 4 quarts inside of their gallon. And the measurements, and they show how they're sort of related to one another. Wonderful visual imagery. That teacher that she had that year had artwork all over the room. And it was these, right, for a period of time, probably during a parent-teacher conference time, and then sent home afterwards. And so it was a great visual representation and artwork display. Of course, these units are really challenging. That's why we get the cool picture, right, is to try to remember them, because it's not intuitively easy to remember all of the different conversions. However, if you're working with units of volume and metric, they're easy because, again, they're all based on powers of 10. So you have all of these different metric units of volume listed here. A couple of things that show conversions that you may or may not have thought about. So, for example, let's just look at the top down first. We have 1 cubic meter, right, or 1 cubic centimeter, and that's 1,000 cubic meters. But you see right next to it, that's also the same as 1 milliliter. In other words, it's a good unit of measure to remember that 1 cubic centimeter is the same as 1 milliliter. That's the connection between, in this case, a linear measure, right? This is a linear measure, and then it's multiplied by 3, right? It's centimeters, and then it's cubic centimeters. And you have over here a capacity measurement, milliliters. So there's a relationship between our linear cubic measurements and our capacity measurements here. So I would like for you to keep those handy as you're looking through example number 3. Some of them are going to be measurements that we can adjust in terms of metrics, others in terms of the standard measurements from the first slide. So we're going to use this one right here, and we're going to use this one right here, the units of volume in both of those capacities. And our examples, we have several. As we work through them, I'm going to do fences on them because I think it helps to keep our data organized pretty well. It says to find the following equivalents. So they show you where you start, in this case cubic meters, and they show you where you end in terms of liters. And if you have the ability through one of your measurements to go straight there, that's great. You won't always, but oftentimes you do. So we would like to look, and this is in units of metric, right? These are metric units. It says meters and it says liters. You're wanting to look over on this table, because these are our metric units, at the ability to change from meters cubed into liters. Do you see anywhere on there where it takes meters into liters? Emily? The second one? Okay, so let me clarify what you're thinking, I think, is that there's not a direct correlation, but we might be able to use the second line on there to do some kind of conversion. Does that sound right? I agree with you. There's a couple of different ways we could do it. We could start with the third one where it's giving me meters cubed. Or we could start with, whoops, sorry about that, this one right here, the second one where I've got liters written over here. So we have a couple of different places we could start. Emily, you mentioned the second one, so we're going to do that one, okay? So Emily mentioned that we could take that second line where it takes this liters right here as my final step, and it shows corresponding amounts that are equal to each other. So this one actually has centimeters cubed here, or you can use decimeters cubed over here as your reference point. So it doesn't matter which one we want to use, we can use either. So we're going to change our cubic meters, so 4.6 meters cubed, and we need to change it into either decimeters or centimeters. Which one would you like to do? Centimeters. Okay, so what is the relationship, and it's not on the table before directly, but we talked about it before, at least I don't think it is, the relationship between centimeters and meters. Do you guys remember? What's the relationship between 1 meter, let's just use 1 meter and centimeters? 1 meter is 100 centimeters, right. So I need the meters on bottom for them to cancel. And this is 1 meter cubed. So I need 100 centimeters, but I need that to be cubed. I'm going to have to cube my 100. Okay, so we'll do the cubing of that in a moment. Once I have it cubed, continuing on with my fence over here, I will have my centimeters cubed on bottom now to cancel out. And then I can use that second line that Emily talked about. And it says that 1,000 centimeters cubed is 1 liter. So if I put 1,000 centimeters cubed on bottom, I can put 1 liter on top. And at this point, the units are going to cancel, right? Here's meters, there's the centimeters cubed, here's the centimeters cubed, and I will end up with liters. So my units do work out properly. I need to be a little more careful with my values and what's being multiplied and divided. So I have the 4.6. I have 100 cubed, which you could either write out as 100 times 100 times 100, or you can write out as the grand total of what that actually is, which is, do you know? It's 1 million, yeah. So if you wish, you can write this as 1 million. Either way is fine. And it's over 1,000. Now, what I'm about to do only works because everything's multiplied or divided, right? There's no addition or subtraction. And also because there are zeros. The zeros can cancel on each end. So 3 zeros in the denominator would cancel with 3 zeros in the numerator. That doesn't work with any other number. I had a student once write a whole bunch of 9s, and they canceled with a whole bunch of 9s in the denominator at the end of numbers. Doesn't do that. This is a zeros property only. But this is what you would have. You would end up with the 4.6. You'd end up with the 1,000. And that would give you what? Yeah, 4,600. And you don't have to do all of that by hand. I did all of mine by hand. If you want to grab your calculator to do the multiplications out, that's fine. Hannah?
Would you think that it'd be easier to do the decimeters instead of centimeters? Like, it'd be easier?
It would keep numbers a little smaller.
Yeah.
Yeah.
Because decimeters equal meters. Or-
Yeah, it would keep all the numbers a little bit cleaner throughout, a little bit smaller if we used decimeters. I think the hang up for us too, because like I have centimeters written down too, like Emily suggested, is that centimeters is a more common measurement for us to think about. And so I think we sort of have this tendency to be drawn to them, but either one will work. The decimeters would certainly work a little bit shorter, a little cleaner. Yeah. Okay, you ready to do part B? Okay, any questions on A before I move on? Oh, I need to stop. We need to do group work. Okay, we'll start with part B next time. So sorry, I forgot to look at the clock.